Welcome to the University Utara, Malaysia School of Computing. Today's lecture focuses on linear models in cybersecurity analytics. Modern threat detection cannot rely on human monitoring alone. Building automated security systems requires us to mathematically model the relationships between different network variables, allowing us to identify threats as they occur. However, analyzing these threats requires two distinct computational approaches, depending entirely on the goal of the system. The first approach is prediction. This involves forecasting continuous, open-ended metrics, like estimating exactly how much network traffic a server will process tomorrow. The second approach is classification. This requires the system to make strict, discrete binary decisions, such as determining whether a specific data packet is a malicious attack or simply normal traffic. To execute these two distinct approaches, engineers rely on two foundational statistical algorithms, linear regression and logistic regression. Understanding the mathematical divergence between these two models is required to build functioning threat intelligence architectures. Linear regression maps network telemetry, plotting traffic volume against detected attacks to fit a straight line, modeling their relationship. This line's equation uses x for the input feature and y for the predicted output. The slope dictates the input's impact, while the intercept establishes the baseline. Mathematically, this model demonstrates that as traffic volume increases along the x-axis, the predicted number of attacks increases proportionately along the y-axis. Security analysts apply this continuous model to forecast heavy network loads and estimate overall system risk levels over time. But this specific approach has a structural limitation. It rigidly assumes the relationship between data points is always linear. Because it draws a single, rigid line of best fit, a handful of extreme statistical outliers can easily drag the slope and distort the entire prediction. While linear regression excels at predicting infinite, continuous metrics, its unbounded geometry creates a mathematical failure when applied to tasks requiring strict boundaries. Many of the most critical cyber threats do not occur on a continuous spectrum. They exist as strict binary states. An event is either an active attack, designated as a 1, or normal traffic, designated as a 0. Tracking intrusion detection data collapses the y-axis to two states, 0 or 1, leaving the middle empty. Applying a linear model draws a straight line directly through this void. This fails mathematically, as the line extends infinitely, breaking well past the strict boundaries of 0 and 1. This breaks the logic of the system. An algorithm cannot output a negative probability, nor can a security interface understand a 1.5 probability of an attack happening. A continuous straight line is incapable of predicting bounded binary states. To fix the system, engineers must alter the base mathematics. The mathematical solution to this binary problem is logistic regression. Applying a sigmoid function bends the line into an S-curve, flattening perfectly at the 0 and 1 thresholds. This confines predictions strictly between 0 and 1, functioning as an exact probability. To achieve this, the linear formula becomes a negative exponent in the denominator. Instead of predicting absolute numerical values, the model uses the exponent e to transform the linear relationship into a probability distribution. Firewalls require binary instructions, not probabilities. We introduce a decision rule setting a strict mathematical threshold at 0.5. If the calculated probability exceeds 0.5, the system automatically classifies the event as an attack. If it is lower, the event proceeds as normal traffic. Let's apply this applied mathematics to a specific cybersecurity task, automated phishing detection. When an incoming email hits the server, the system scans the content, extracting specific input markers, like a suspicious hyperlink or an unknown sender domain. The algorithm processes these extracted markers as its x variables and runs them through the logistic equation. The math computes the variables and yields a final probability score of 0.85. Because 0.85 crosses the 0.5 threshold, the decision rule triggers. The firewall drops the gate and classifies the email as malicious. By bounding linear mechanics inside a logistic curve, engineers engineered a precise mathematical engine capable of automated threat classification. This comparison table breaks down both models. Linear regression yields continuous numerical values, while logistic regression yields bounded binary probabilities. This dictates their use cases. Linear models handle broad prediction, logistic models execute strict classification. Linear forecasts daily attacks. Logistic decides if an event is an attack. Enterprise security environments do not choose between these algorithms. They deploy them simultaneously. This flowchart illustrates a unified risk scoring system. Incoming telemetry splits into two concurrent branches. The linear model processes the data to predict the overall scale and volume of risk to the network. Concurrently, the logistic model acts as the gatekeeper, making discrete, binary decisions on the presence of individual threats. For computer science students at UUM, mastering these fundamental statistical models is the absolute prerequisite for designing advanced, intelligent cybersecurity architectures.